This section covers the fuel system features, overall fuel flow in ISB engine, and the fuel timing. Click on the area you want to learn about. In this section, we will look at various features of the ISB engine fuel system. Click on the item you want to learn about. The ISB engine utilizes a 12-volt DC electric lift pump operated by the ECM and has a minimum operating pressure of 10 psi while the engine is running. The lift pump should operate at approximately 7 psi maximum pressure during cranking to facilitate good startability. The lift pump is controlled by the engine ECM, which provides a PWM signal for lift pump operation. The lift pump is self-priming on the low-pressure side of the fuel system. When the key is first turned to the on position, the lift pump operates for 2 seconds. During cranking, the lift pump operates at a limited duty cycle to control injection pump inlet pressure until the engine starts. After terminating cranking, either momentary or continuous cranking, the lift pump operates for 25 seconds with the engine not running. The running engine, the ECM commands the lift pump into a full duty cycle mode operation. If the engine stops without the key being turned to the off position, the lift pump shuts off to prevent fuel leakage if a broken fuel line is the cause of the shutdown. A built-in 582 mesh removable cleanable pre-strainer is installed in the pump. Take care not to disturb the lift pump vanes when removing the screen. 2 different style fuel filter water separators are available for the ISB engine, a removable cartridge filter and a spin-on filter. Each of the different filters has the same specification. The top-load filter design is used on many ISB engines. This filter utilizes a new filtration media contained in a removable throwaway cartridge, which significantly reduces the cost of a filter change. Always replace the filter cap O-ring and install the filter onto the cap before inserting it in the canister. The reusable filter housing contains an integrated water-in fuel or whiff sensor, fuel heater, and water drain assembly. The filter causes water to precipitate out of the fuel and drip to the bottom of the housing. The sensor becomes immersed in water. The whiff sensor alerts the operator to water in the fuel filter housing. The water may be drained from the fuel filter housing using the easy lift handle. Release handle when fuel begins to flow. The fuel heater warms the engine fuel in cold weather conditions to provide improved flow through the filter in these conditions. A bimetallic snap switch in the heater turns the fuel heater on when the fuel is below 40 degrees and turns the heater off when the temperature of the fuel at the sensor reaches 80 degrees. Although many applications use the replaceable cartridge-type filter, some applications utilize a convenient spin-on filter assembly. Spin-on fuel filter assembly contains a whiff sensor and water drain, but in a different arrangement from the replaceable cartridge filter. With this style filter, the fuel heater is mounted on the filter head. The fuel pump drive gear is driven at half-engine speed by the front gear train. Keying fuel pump drive gear to the fuel pump shaft and aligning the timing marks on the fuel pump drive gear to the camshaft provides a positive location for fuel pump installation and simplifies fuel pump timing. The Bosch VP44 fuel pump is an electronically governed distributor fuel pump. This pump provides immediate fuel quantity response due to electronics. Electronic pump calibration provides for more consistent fuel pump delivery at manufacturing and over the life of the fuel pump. Fuel pump fault status, fuel temperature compensation, and the ability to make rapid changes in fuel delivery to maintain the desired RPM. A fuel temperature sensor located in the top of the fuel housing determines the temperature of the incoming fuel. This is used by the FPCM to alter fueling quantity accordingly as the fuel temperature increases. Maximum fuel inlet temperature should not exceed 160 degrees Fahrenheit. Bosch injector used on the ISB engine is a hole-type nozzle design. An O-ring seal on the injector body separates the fuel manifold from overhead engine oil. A sealing washer is installed on the injector tip to seal the cylinder. This washer establishes the vertical position of the injector for alignment with the high-pressure fuel connector. The injectors are located under the valve cover between the rocker levers and are installed in the center of the combustion chamber. The shape of rocker levers allows the injector to be removed without disturbing the rocker adjustment. The slot in the top of the injector and the hold down are offset to orient the injector in the correct direction. This ensures that the supply hole in the injector is aligned with the fuel connection that allows the fuel to flow from the high-pressure fuel lines. In this section, we will look at the fuel flow through the ISB engine. Keep in mind that the fuel also provides lubrication and cooling within the fuel system. The electric fuel lift pump draws fuel from the fuel supply tank and supplies low-pressure fuel to the Bosch fuel pump. This pump provides a positive flow of fuel to the filter head. Fuel flows through the filter head and into the combination 5-micron fuel filter water separator. After water and contaminants are removed, the filtered fuel is transferred to the distributor pump through the low-pressure supply line. The electronically controlled VP44 pump pressurizes the fuel, controls timing, meters an amount of high-pressure fuel, distributes the fuel to each of the 6 high-pressure fuel lines and to the injectors. The major components of the fuel pump include the housing, vane pump, main drive shaft, internal cam ring, shoes and rollers, support bearing, rotor, pumping plungers, high-pressure head, metering control valve, delivery valves, master timing piston, master piston control valve and spring, master piston spring, servo spring, servo piston, servo cylinder, pressure regulator, ECM, incremental angle timing sensor, metering control valve coil, and the timing control valve. All these components assemble to make up the VP44 fuel pump. Fuel flow in the fuel pump begins as fuel enters the fuel pump at the outboard rear fitting near the fuel pump control module, or FPCM. The fuel flows in this cavity to cool the FPCM electronics. The vane pump is driven by the fuel pump drive shaft. The blades of the vane pump draw fuel through the inlet slot in the pump. As the vane pump rotates, fuel is transferred from the inlet port to the outlet port. The volume and fuel pressure delivered by the vane pump increases in accordance with the engine speed. The vane pump then delivers the fuel to the pressure regulator near the top of the pump. The pressure regulator located after the outlet port controls the vane pump pressure to the fuel and timing control devices. Excess volume is routed back to the inlet side of the internal vane pump. This regulator controls vane pump pressure up to approximately 300 psi at rated speed. This vane pump pressure is delivered to the metering control valve through a fill slot in the pump rotor. When commanded by the FPCM, the metering control valve opens and allows fuel to flow through the discharge port and through the center of the delivery valve to the high-pressure fuel lines. If the pressure is high enough, the vane pump pressure opens the delivery valve. The delivery valve is vented, therefore a small amount of fuel will always flow through the valve. Additionally, this fuel pressure completely fills the 3 high-pressure pump chambers. Excessive pressure during cranking can cause this pressure to hold high-pressure plungers in and not acquire a full charge of fuel. This is why the fuel lift pump operation is limited until the engine starts and the vane pump can produce enough pressure to exceed the pressure of the fuel lift pump. Excessive lift pump pressure can cause the engine to be difficult to start. The fuel pressure pushes the plungers, rollers, and shoes out. At this time, the FPCM commands the metering control valve to close, trapping the fuel in the high-pressure chamber. As the rotor turns, the cam lobes force the rollers and shoes against the plungers, causing the pressure to increase in the high-pressure chamber. As fuel pressure rises, the fuel continues to flow through the discharge port onto the high-pressure injection line. Pressure increases until the needle valve in the injector lifts at approximately 4,500 psi and injection begins. Pressure continues to rise due to the size of the holes in the injector nozzle, not allowing fuel to flow out of the injector as quickly as the plungers are forced in by the cam ring. This pressure can reach approximately 20,000 psi at maximum fuel flow. Fuel delivery continues until the FPCM commands the metering control valve to open. This provides an alternate path for the fuel flow, thereby quickly reducing the pressure in the high-pressure supply line and ending injection. ECM determines the fuel quantity needed based on the engine speed and load. Based on this signal from the ECM, the FPCM has the ability to vary when the command is sent to open the metering control valve and end injection. This allows the FPCM to vary the quantity of fuel delivered. In summary, the high-pressure chamber is filled when the meter valve is open, the valve is then closed, and injection begins. The length time the metering valve stays closed determines the amount of fuel injected. As the high fuel pressure is created and controlled, a significant amount of heat is generated. Cooling passages are designed to carry this heat away from the pump components and out of fuel pump to the fuel tank return line. This return flow volume is controlled by an overflow valve externally mounted on the fuel pump in the return line. Approximately 70% of the fuel flow is returned to the fuel tank. The overflow valve maintains a small pressure in the fuel pump return flow through the use of a check ball. This check ball opens at approximately 14 psi. Vent drilling in the fuel flow path before the check ball allows the system to purge out air. Any internal fuel leakage is returned to the inlet side of the vane pump. From the fuel pump, fuel flows through the high-pressure fuel lines connected to the pump to provide the desired 1-5-3-6-2-4 firing order sequence. The pumping cycle is repeated for each cylinder. The internal dimension, rigidity, and length of the high-pressure fuel lines is critical for proper fuel delivery. From the high-pressure fuel lines, the fuel travels to the fuel connector installed in the cylinder head. This connector provides a flow path between the high-pressure fuel line and the injector fuel supply location in the injector. An edge filter installed in the fuel connector breaks down any debris remaining in the fuel before it enters the injector. Connector to injector seal is maintained through the flare fitting on the connector and the angled seat on the fuel nut port in the injector. Torque on the high-pressure fuel line fitting holds the connector in position. Bosch hole-type injectors are used on ISB engines. The injector assembly consists of the high-pressure inlet, nozzle body, shims, spring, needle valve, nozzle retainer, nozzle, and sealing washer. The fuel flows down the drilling in the nozzle holder and nozzle and enters the needle valve bore. The spring load on the needle valve keeps the valve closed until the pressure rises to approximately 500 psi. At this pressure, the valve lifts to allow fuel to flow into the nozzle tip. The point at which the needle valve lifts is the operating pressure setting. This is often referred to as the pop pressure setting and is set by the shims placed above the spring. During injection, the pressurized fuel is forced through spray holes in the injector nozzle, causing atomization of the fuel for combustion. When the metering control valve in the distributor pump opens, pressure in the nozzle is rapidly reduced, permitting the needle valve to quickly close. This action stops the flow of fuel into the cylinder and prevents exhaust gases from entering the nozzle. Fuel leaking past the needle valve drains through the spring cavity into the fuel drain manifold. An O-ring on the connector acts as an external seal for the fuel drain manifold. An O-ring at the top of the injector provides a seal between the engine oil and the fuel drain manifold, and a copper sealing washer provides the combustion chamber seal. This small amount of leak-off from the injectors flows to the injector drain manifold integrated as a drilling in the cylinder head. Fuel from the overflow valve and return fuel from the injector drain are combined, and return fuel flows to the fuel tank. As shown in the fuel flow section, the high pressure needed for injection is created by the rollers, shoes, and plungers being pushed in by cam loops with the rotation of the rotor. Changing the position of the cam ring changes the timing of injection. The position of the cam ring is controlled by the position of the master piston in the fuel timing mechanism. During cranking, the return spring holds the master piston and cam ring in the retarded position, beginning injection at approximately top dead center. The vane pump pressure generated by the vane pump is delivered to the master piston control valve and the servo. As this fuel pressure increases, the pressure on the end of the master piston compresses the return spring and moves the piston toward the spring. This causes the cam ring to rotate and advances the injection timing. In this position, the rollers contact the cam lobe sooner, which initiates delivery earlier in the cycle. The flow of supply fuel to the master piston is controlled by a master piston control valve and servo piston in the timing mechanism. At startup, the spring on the servo piston holds the piston in its extended position. This forces the master piston control valve against its spring pressure and closes off the flow path through the master piston. Fuel vane pump pressure is directed to a chamber inside the servo piston. As fuel vane pump pressure builds, the servo piston spring is forced to compress. This allows the spring on the master piston control valve to open the passageway for the fuel vane pump pressure to move the master piston and advance the timing. The fuel flow through the servo piston is controlled by the timing control valve. When in its normally closed position, the timing control valve closes off the flow path for the supply fuel. This allows the fuel pressure to build and compress the spring in the servo valve. This allows the master piston control valve to open and fuel flow to the end of the master piston, moving the piston to advance the engine timing. However, when commanded by ECM, the timing control valve opens and allows the fuel vane pump pressure to flow out of the servo piston. This allows the spring in the servo piston to extend the pin. The pin then causes the master piston control valve to close. This shuts off the fuel flow path. The return spring causes the master piston to move and rotate the cam ring to the retarded timing mode. The ECM timing calibration sends a signal to the timing advance mechanism to provide variable fuel injection timing between 30 to 0 degrees to match the engine speed and load ranges for maximum performance and emission control. Timing advance is also a function of fuel pump speed and fuel vane pump pressure. The ECM receives sensor inputs for injection timing calculation from the boost pressure sensor, coolant temperature, engine speed sensor, intake manifold pressure sensor, and throttle pedal. Timing at any given RPM and load can be varied due to these inputs. ECM then calculates the desired timing command based upon internal algorithms and sends a signal to the FPCM. A number of factors influence timing and quantity of fuel injected. Some factors take precedence under certain conditions. For example, low coolant temperature prevents the engine from going to full throttle regardless of the input from the other devices. The fuel pump increment angle time system determines the beginning and end of fuel delivery based on the pump angle. This system utilizes a sensor to generate pulses from the teeth on a ring gear installed on the drive shaft. This gear has a missing tooth corresponding to a specific engine position. In conjunction with the ECM, the information provided by this system allows FPCM to determine engine position and control the fuel timing. The FPCM then sends a signal to the timing control valve to adjust the timing.